Hello again and welcome to Virtual Crafts. In the last video we saw how we can design a half adder in system Verilog, and in this one we'll just move on and see how we can design a full adder in digital system design. Now the approach that I'll be using to design a full adder in this video is to design the full adder by using two half adders, which means that in this video we'll be using the piece of code we written for half adder in the last video. There are other simpler ways to design a full adder too, which I'll explain in some later videos. So without any further ado, let's get right into it. Well, theoretically we saw this is how a half adder looks like. It takes two inputs and gives us a sum and a carry as an output. Now the limitation of a half adder is that it can only add two single digit numbers. To overcome this limitation, we have designed the full adder, which is basically the combination of two half adders. So if we connect two half adders in this way, we can get a full adder. As you can see, this is the first half adder, this is the second half adder, and with an additional OR gate, we can get a complete full adder. As far as the truth table is concerned, this is what the truth table of a full adder looks like. Now we have three number of inputs to the adder, and you must be wondering what the Cin is in this truth table. Well, when we are adding multi-bit numbers, single digit numbers can have a carry out, as we saw in the last video for half adder. Now that carry out is the carry in for the next bit in the multi-digit number. So that's enough for the theory. Let's dive into the implementation. Alright, I'll go ahead and create a new project. I'll give a name to this project, which is full adder, and I'll go ahead and click OK. Okay, the project has been created. Now we need to add the files to this project, and as I mentioned in the last video, we need two files, one for the design and one for the test bench. So I'll create a file for the design. I'll change the extension to system Verilog. Okay. And I'll create another file for Testbench. That's it. These are the two files I need. I'll click close. And as I mentioned in the last video, I prefer to use another better code editor than these tools. So I'll just go ahead and open VS Code and edit these files there. If you don't have another editor, just write your code in Questa itself. That's perfectly okay. Alright, before I get started with the implementation, let's see what will our strategy be for the implementation. This is what the block diagram of full adder looks like, and if we label the intermediate wires, this is what we get. As for the first half adder, when A and B are added, we get the intermediate sum and the intermediate carry. Then for the second half adder, the inputs are the intermediate sum of the first half adder and the carry in of the full adder. And this gives us the sum of the full adder. For carry out of the full adder, we need to OR the carry of first half adder and the second half adder, and that gets us carry out. So now let's dive into the implementation. Okay, here I am. I'll go ahead and declare the module. I'll add the ports to it. First we'll add the three inputs. And now the two outputs of the full adder, which will be sum and carry out. Alright, so this is the module wrapper. So now before proceeding, we need to use the half adder design from the last video. So I'll just go ahead and paste that design here. So this is the code we wrote for half adder in the last video with the test bench. If you have not seen that video, you can go ahead and check it out. And now we will instantiate this half adder module in our full adder. So let's do it. Let's give a name to the instantiation. This is our half adder 1, so something like this. And here we'll connect the ports. And we need two half adders, so I'll instantiate another half adder here, half adder 2, and we'll connect the ports in a while. So for the first half adder, the inputs will be A and B, and the outputs will be S1 and C1. Now we don't have S1 and C1 as our port. Those are local wires, so I'll go ahead and create local wires here. Simply logic S1 and logic C1. Okay, now let's go ahead and connect the ports for the first half adder. These are the two inputs. The half adder port sum will be connected to our local wire S1, and the half adder port carry will be connected to the local wire C1. So this is it for the first half adder. Now A and B will be fed to this half adder as inputs, and we will get S1 and C1 as sum and carry respectively. For the second half adder, the inputs will be S1 and the carry in, and the outputs will be the sum and C2. Now C2 is again a local wire, so I'll just create it. Another logic here, C2. I'll connect the first input to S1, which is the output of the first half adder. I'll connect the second input to Cin, which is port to the full adder. The sum will be connected to the sum of the full adder, which is the final output, and the carry will be connected to C2. So the second half adder gets S1 as the input and Cin as the input, and it gets a sum as the output and the intermediate carry 2 as the output. Now for our final move to get the carry out, we need to OR the carry of the first half adder and the second half adder. So I'll go ahead and I'll create the C out simply by ORing the C1 and C2. So this is pretty much it for the design. Now let's go ahead and write the code for the test bench. Now our test bench will have local wires to drive the stimulus to the design, so I'll just create them. Okay, so this will be our stimulus, the 3 inputs and the 2 outputs. Now we will instantiate our design in here. I'll name the instantiation, let's say FA. And now let's connect the ports. I've again kept the name same for simplicity. And now let's drive the stimulus to the design. I'll go ahead and create the initial block, and the first set of inputs will be all zeros. And now after a unit delay we will observe the outputs. Let's say 5 nanoseconds. I will add a display as we did in the last video to monitor the outputs of the design. So what we need to display is the 3 inputs. And the 2 outputs. So this is the first set of stimulus from our truth table. If I go ahead and look at it, this is what it looked like. All the three inputs for the first set are 0, and against this combination the outputs should be 0 and 0. So I'll go ahead and list all these combinations real quick. Okay, so now I'll change the stimulus for the other combinations. This will be 0, 0, 1, 0, 1, 0, 0, 1, 1. You can look at the truth table while giving the stimulus. 1, 0, 0, 1, 0, 1, 1, 1, 0, and lastly all ones. So this is pretty much it. This is the test bench for the full adder. I've saved both the files. Now let's go to the QuestaSim and simulate the design. I'll select both the files and compile them. Now both the files have been compiled without any error. If you have any compilation errors in the files, you'll see them here and then you can resolve them. Now I'll go ahead and click simulate. I'll choose my test bench from here and click OK. I'll select all these inputs and outputs and I'll add them to wave. Let's move the wave to a new window to clearly see it. Now before running the simulation, I'll go ahead and change this time to 5 nanosecond as I did in the last video, because in the test bench I've mentioned 5 nanosecond as the unit time for displays. So let's go and run. I'll zoom in. Again, here as we can see that for the three inputs when they are 0, we get 0 as the sum and 0 as the carry. For our next combination, you can see that the carry in is 1, the input combination is 0, 0, 1. We get sum as 1 and C out as 0. You can compare this to the truth table. For the next combination, we have B is 1 and carry is 0, so we again have the sum as 1 and carry out as 0. For the next combination, we have both B and carry in as 1. We have sum as 0 this time, and now the carry out is 1. Now we have this combination and the sum is 1, and if I go ahead and simulate the next three combinations, this is what we have. And for the last combinations, we have all inputs as 1 and both the carry and the sum are 1. And this can be verified from the truth table here. So you can tally the truth table and the waveform by pausing the video anywhere. Now let's check the output console to see the displays that we added in our test bench. And this is the truth table printed here. When we have all three inputs as 0, we get sum and carry as 0. And this is again the whole truth table. You can go ahead and verify it from there. So this is it. This is how you design a full adder using two half adders. In the next video, we'll see how we can design a full adder using behavioral coding. So this is it for this one. If you like this video, please consider subscribing and hit the bell icon next to it, because there is a lot coming in your way. Thank you and see you in the next one.